Maybe I'll start by telling you something that, by talking to a couple of you, I realized that I should have made more explicit. I told you that lattice ideals had a lot to do with toric ideals, and if you look in the literature, there's much more about toric ideals than about lattice ideals. So maybe I just want to clarify that. We have associated to a commutative, finitely generated semigroup with 0 this thing, and we have called it the lattice ideal. Okay. So what's a toric ideal? A toric ideal is exactly this construction when this guy happens to be an affine semigroup. So Q affine if Q is affine, then IL is called a toric ideal. Okay. So you see, toric ideals are nothing new. We have been talking about them this whole time. Because actually, if you think about it, all but one of the examples that I have done of this setup have been for affine semigroups. Right? I always want to be able to draw these things in the plane or on the line or in space in Zn for some n. The only example where we did not have an affine semigroup was when we did this over Z mod 2. And in that case, we don't get a toric ideal, we get a more general thing called the lattice ideal. But this whole theory that we have done here applies to toric ideals. Okay?
So how does that relate to components? Why is it called a toric ideal?
It's a longer answer than I want to give you right now. But
So there is some relation there.
yeah. I'm sorry? Yeah, a couple of chapters later. I mean, it has to do with toric varieties, basically. So varieties are this general thing in algebraic geometry, and they're very difficult generally. And then there's this special family called toric varieties, which are much simpler and much more combinatorial. And this has a lot to do with that. So that's why. Okay, so we have been talking about, last time we talked a little bit about the next plan, which is that given a lattice ideal, okay, so we have Q a semigroup, then we use it to get our lattice ideal, and now we want to know how to deal with this guy, right? And we said that one of the ways of dealing with it was by taking the initial ideal and making it monomial. Okay? And so we started setting that up last time. So what we said is that if I take a weight vector, right? And the way that I think about this is that if this lives in Z n, so this lives in ZD. The lattice ideal is in the polynomial ring on m variables. And then I give a weight to each one of the variables, right? Where remember, n is the number of generators of the semigroup. Okay? So maybe I can write it like this. Q is the semigroup by the natural combinations of A1 up to AN, and this is in RD, in ZD. Well, I guess I don't necessarily want to say that it's in ZD. If I say that it's in ZD, that means it's affine. In general, this lives in the abelian group A that we talked about. Right? Anyway, so the point is that I give a weight to each one of the variables, and then I want to study two things. So the goal for today is to describe two things. One thing is the initial ideal with respect to this W. And the other thing is what I call the initial complex. So this is the initial ideal. And this is the initial complex. And we said that this is the guy whose Stanley-Reisner ring is the radical of that initial ideal. Okay? And that's our goal for today, is to describe these two things explicitly. So the first thing that I want to do is talk about how to describe this initial ideal. Okay? And I want to do it in an example first, and then we will give a general discussion. Okay? So let's do it in this example. Let's consider the semigroup in Z1 generated by these numbers. So those numbers look familiar to everyone in this room because these are the four denominations of coins in the US. I could possibly put 100 and 200, I guess, because there are $1 and $2 coins, but let's leave it at that. So in Colombia, I would use different numbers, but anyway. So this sounds like a joke, but it's serious. You'll see that I have a point here. So this is my semigroup, okay? So what's the lattice ideal? Do you guys feel prepared to write the lattice ideal without writing the lattice? I mean, we always do this, right? First Q, then the lattice, and then the lattice ideal. And the lattice is the lattice of relations among these things. And then we take the lattice ideal, which is turning that into polynomials. I'm going to be bold, and I'm going to do this already for the polynomials. But remember that basically every generator here describes a relation between these four guys. Okay? And I could call them A1, A2, A3, A4. Okay? So give me some relations between these things, between these four vectors. A vector here is a number. So what's a linear relation between A1, A2, A3, and A4? For example, 5A1 equals A2. Right? 5 pennies make a nickel. How do we write this in the ideal? We want to write it as exponents, right? 5 pennies equal 1 nickel. And to actually keep track of these things, I'm going to change the names of the variables, and I'm going to call them P, N, D, and Q. Okay? And that way we will, but maybe for the Colombians, I'll write here P equals penny equals 1 cent, N equals nickel equals 5 cents, D equals dime equals 10 cents, and Q equals quarter, 25 cents. And so now I write that 5 pennies equal 1 nickel. Okay. What else? For example, 1 dime equals 2 nickels. I actually have trouble remembering which one is nickel, which one is dime, so let me know if I say something wrong. What did I say? 2 nickels equal 1 dime. Okay. What else? N nickel, and 2 dimes give me a quarter. And how do I write that? This is supposed to be a monomial, right? On one side I say 1 nickel and 2 dimes, and on the other side I say a quarter. Okay. Anything else? There's many more relations, right? I could say, 2 quarters equals 5 dimes. But it turns out that actually these 3 generate all the other relations, and it kind of makes sense because basically I'm telling you how to express each currency in terms of the smaller ones. Right? So for example, it's also true that a dime is equal to 10 pennies, but that's a consequence of a dime being 2 nickels and a nickel being 5 pennies. In other words, if this lives in an ideal and this lives in an ideal, then automatically p to the 10 minus d is going to live in that ideal as well. And so this is my lattice ideal, and actually this is a very good thing to keep in mind when you think about toric ideals in general or lattice ideals. Each one of these monomials is kind of giving you an exchange rule between how many vectors a1 and a2 and a3 do I need to exchange with how many vectors so and so. Okay, so we have this, and now we need a weight vector. So I could choose any weight vector, but let me choose 1, 1, 1, 1. Okay? And I need to describe the initial ideal. Okay? How do I do that? Well, the first thing I need is to find the Grosvenor basis with respect to that W. Okay? So the reduced Grosvenor basis for I sub L with respect to W equals 1, 1, 1, 1 is the following. You just feed this into the computer. And we know how to do this by hand, and we know that it's better to do it on a computer, right? I think you're convinced of this by now. It turns out that you need one more thing here. How do we do this? We do this as polynomials, and we find that there's something we can't reduce. And the guy that we cannot reduce looks like this. And now when you compute all the S polynomials between these pairs, you find that they're all 0 mod those guys. And so these 4 right here form the reduced Grosvenor basis that we need. Okay? And given this, we can immediately write down what the initial ideal is. Okay? All I need to do is look at each one of these guys and say what its initial term is. Okay? So what's the initial term here? Is it p to the 5 or is it n? Well, the weight is 1, 1, 1, 1. So every variable has weight 1. So this has weight 5. This has weight 1, so this guy wins. This has weight 2, and this has weight 1, so this one wins. This has weight 3, and this has weight 1, so this one wins. And this has weight 3, this has weight 2, so this one wins. Okay? So that means that my initial ideal looks like this. Okay? That's what it is. And now what I want to do is use our intuition from using these coins to figure out what this all means. Okay? For example, what am I really saying when I say choose this or choose this? Okay? What is the weight of a monomial here? Let's say I have a monomial like p to the 7 n cubed. See, I can get it right. D 5q squared. What is the weight of this monomial? It's 7 plus 3 plus 5 plus 2 equals 17, but what are we thinking of as a monomial here? A monomial is saying I have 7 pennies, 3 nickels, 5 dimes, and 2 quarters. And the weight is just the number of coins. Okay? So what I want to say is that a monomial here correspond to a bunch of coins, pennies, nickels, dimes, and quarters, okay? And the weight of the monomial is the number of coins. Yep. So now what am I saying here? I have these binomial things, and I want to say, which one is the initial term? Is it this one or this one? Well, really what I'm asking is, here I have 5 coins, here I have 1 coin. What's better? And well, it depends what you're trying to do. But basically, you're just choosing which of the two sides has more coins. Okay? 5 coins versus 1 coin, 2 coins versus 1 coin, 3 coins versus 1 coin, and 3 coins versus 2 coins. Okay? So given that, what can you tell me about these 4 generators in terms of coins? I'm sorry? And in a way, this means 5 pennies, right? Which is more than I could do with 1 nickel. This means, for example, what does this mean? This means I have 3 dimes, but the thing is that I have a better way of producing 30 cents, which is to use a quarter and a nickel. And so if you think of what these things are, these are basically non-optimal ways of making exact change. Right? I mean, that is what it is. So the terms, let's put it in this way. I mean, elements of, let's say, the generators of isobel correspond to 2 ways of making the same amount of money. Right? And the elements of the initial ideal are, I mean, what's a monomial element of this? It's just a multiple of this. And if you're a multiple of something like this, that means that you can't be an optimal way of making the exact amount either, right? For example, this thing is not the optimal way of making however cents this makes, because it's a multiple of p to the 5, and that means that we could exchange the 5 pennies for a nickel and use fewer coins. So monomial elements of the initial ideal correspond to non-optimal ways of making exact change. Okay, so let me read this for you. Non-optimal ways of making exact change. And given this intuition, we can now make a theorem. And this theorem is true not just for the setup, but for any setup. Okay? So what am I doing in general? In general, I'm going to make a definition. Say that some vector is not optimal with respect to my weights if there is basically a cheaper way of making that exact change. And what this means is if there is v and n to the n such that u minus v is in the lattice. In other words, x to the u minus x to the v is in the ideal, and the weight of v is less than or equal to the weight of u. Is less than, strictly, the weight of u. Okay? So you see I'm saying exactly the same thing. U is not optimal if I can perform the exchange from u to v, thereby making a cheaper way of the same number of dollars, which in this case is not a number, but a vector. Okay. And with this definition, I have a theorem which says that the initial ideal is just the span of the not optimal monomials. Yep. And the proof is basically just repeating all the words that I said here and just making it into math symbols. But really, that's the content. Okay, I hope you believed what I said here, and if you believed it, then the proof is identical, and you get this. Okay. I really think it's worthwhile for you to really work this out. Maybe for, what's a good example? Maybe that example that we keep doing. Okay. Then the one generated by 3, 0, 1, 1, and 0, 2. Okay. So what am I thinking here? I'm thinking somehow that these are like my coins. I have a 3, 0 coin, a 1, 1 coin, a 0, 2 coin. And I want to use those coins to make a certain quantity, but a quantity is now a vector. Right? And I'm asking for the optimal way of, maybe let's spell this out actually. Okay. So goal. So here's an optimization problem. Given some vector AB, write it as a combination of these guys. Well, I have to give you a target vector, and I have to give you a weight function. Right? Because there our weight function was 1, 1, 1, 1. Okay? But here I have to give weights to x, y, and z. Okay? And so the optimization problem is, given a vector a comma b and weights, which maybe it's better if I call, since we've been calling this a1, a2, and a3, maybe it's better if I call them 1, 2, and 3. Okay? So in that case, they were 1, but here I might say, this is going to cost you 2, this is going to cost you 1, this is going to cost you 7. Okay? The question is, how can you write a comma b as a combination of these 3 guys, but this costs you 2, this costs you 1, and this costs you 7? So that 2x plus, well, w1 x plus w2y plus w3z is minimum. Okay? If you think about this, this is a question that you would think would belong in a different class, in an optimization class. Yeah? But this is exactly the optimization problem that we're facing here. And the punchline is basically that this optimization problem is exactly the same problem as taking this initial ideal. Okay? So somehow this is algebra. And this is what's called integer optimization. Integer program. Okay. And then the point is that having a dictionary between this algebraic question and this optimization question, you can go back and forth. Okay? So maybe you're an expert in integer programming, like Serkan Hostin is. His PhD is in integer programming. That means that he's really good at toric ideals, and that's what he does. I mean, that's a lot of his research, and he's really one of the experts in this stuff. Okay? And you can take it the other way also, if you, which is also his case. If he knows a lot about lattice ideals, toric ideals, that means that he can solve hard optimization problems. Okay? And you can, and people really use this in practice. If you have an optimization problem, this is a very natural optimization problem, right? Or that one over there. Okay? I mean, this is really a question about what is the way of making change with the least number of coins. That's a very natural question. And we have an algorithm for solving it. The algorithm is this Buchberger algorithm. Okay? So that's a really nice dictionary between the algebra of lattice ideals and these questions in integer programming. So that's the first thing that I wanted to tell you about today. Do you guys have any questions about it? Yeah.
I'm a little confused. If you picked a weight vector that the Q component was, say, everything else was 1 and Q was 5, then it seems like the initial ideal could be not the non-optimal.
So, right. So let's talk about that. What happens if in this example you change W? So maybe, I mean, I don't know, what's one way to put this? You all hate pennies, right? You have mountains of pennies and you want to spend them really badly. Okay? And so one way of stimulating that is just to give them more weight. So you could just say, well, what I want is to spend pennies, so let me change this weight to a weight that makes me want to spend pennies, like maybe 0.5, I don't know. Okay? And so that means that you're kind of counting total number of coins, except that a penny counts for half a coin. Or maybe let's make it more drastic. Maybe you really want to spend these pennies, so you give it a weight of 0.1. That means that all of a sudden in this exchange, this is worth 0.5 and this is worth 1. Which means that it's cheaper for you to use 10 pennies than it is to use 1 nickel. Okay? So by changing the weights, you stipulate basically what you want to optimize. Okay? If you want to optimize number of coins, then you get this initial ideal. But if you measure optimality in a different way, by a different weight function, then you have to do it all over again, right? You have to get a different Grobner basis, which corresponds to that W. And then you're going to get a different initial ideal, which is going to tell you what is not optimal according to that weight. Okay? Your question?
How do you find a Grobner basis corresponding to a weight vector?
It's the same thing as before. You do this pair business. So to find this reduced Grobner basis, you say, okay, well, let me take the S pair corresponding to this and this, and then.
So if we're doing it in a computer, then how do we tell the computer that we want to use a certain weight vector?
If you look it up in the manual, the computer will generally let you specify. I actually feel that computers prefer this instead of reverse lexicographical or anything like that. And surely any algebra system that can compute Grobner basis is perfectly happy for you to feed it a weight vector.
What do you do for ties?
Remember that we've been talking about choosing W's that are generic so that these ties don't come up. If there are ties, then it's a trickier business. Actually, isn't your project about that? I mean, that's it, right? So you're looking at the Grosvenor cones, and so in the maximal dimensional pieces, you're optimal, and in the lower dimensional pieces, you have a little bit more work to do. So you can tell me about that. You shouldn't have asked. No, I mean, I'm happy to talk to you more about it, maybe during office hours. Okay, so for example, what this allows you to do, and I wrote it out here. You can really solve this optimization question using this language just by looking at this answer. So what this answer tells you is the following. So we'll call this a theorem about coins. Theorem about the US coin system. Using I pennies, J nickels, K dimes, L quarters is optimal. And what I mean is minimum number of coins for the desired exact change. If and only if basically you don't want to use more than 4 pennies. You don't want to use more than 1 nickel. And between the nickels and the dimes, you don't want to use more than 2. This is a corollary of what we did here. Okay. Of course, this is kind of a toy example, but I hope this makes it plausible to you that you can actually use this machinery to solve real optimization questions. And again, I know that some of you are planning to do this on the project, so I hope this discussion helps a little bit. Okay, so that describes this initial ideal, and basically it translates it into a question of integer programming. Okay. Now, the other thing I want to do is describe this initial complex. And for that, I need to tell you a little bit about a different topic. I think maybe I said something about this already. Did I? Did I talk about regular triangulations? Maybe I didn't. Oh, no. The thing is that I talked about Hall complexes which have a kind of a similar feel. So I haven't done this concretely, but we've done that which is a little bit similar. So what I want to do is this. Let's say that you have a polytope, okay? And this polytope is given to you as the convex Hall of a bunch of vertices. You have a polytope in Rn. Okay? And then you're giving a height function from V into the reals. Height function on V. Okay? So for each point in V, you specify a height. And then we're going to use this information to produce something called, a way of cutting up the polytope P into smaller polytopes. Okay, so this is going to produce a subdivision P sub H of P. This is just my name for it. Okay. So here's what I'm going to do. What we're going to do is we're going to take this polytope that lives in Rn, and then we're going to take the heights to make this polytope live in one dimension higher. Okay? So, I don't know, maybe P is the convex hull of vectors v1 up to vm. This is in Rn. Okay. And what I'm going to do is I'm going to lift this into one dimension higher using these heights. Okay. I'm going to define a new polytope called p hat. And what I'm going to do is that I'm going to take each vertex. So we're thinking that our polytope lives maybe in the plane. Okay. And then for each one of the vertices, you're going to lift it to the height that h prescribes. Okay. So basically, you get v1 comma height of v1 up to vm comma height of vm. And now this is going to live in r to the m plus 1. You should think that this thing has n dimensions, and this thing has one dimension. Okay? So what's the point then? I mean, we have our polytope here, okay, on a plane. Then you lift each vertex, and now what you get is some polytope that's in one dimension higher. And now what you're going to do, it sounds a little funny, what you're going to do is that you're going to kind of go under the polytope and just look up and see what you see. And I claim that what you're going to see a subdivision of P. So if we look at p hat from below, we will see the subdivision p sub h of p. So before I make any definitions of how this, before I describe precisely what I mean, let's do this in an example. And let's not be too ambitious, so let's start with an example of a one-dimensional polytope. And this one-dimensional polytope, it's on the line, and it's given to me as the convex hull of a bunch of points. Okay? So maybe it's given to me as the convex hull of 4 points. Now that's a little silly, right? Because you don't need 4 points to determine this polytope. But in this setup, you allow having unnecessary points. So these 4 points are V. Maybe we'll call them V1, V2, V3, and V4. And then I need to specify a height function. And maybe the height function will just be, here the height is 2, here the height is 3, here the height is 1, and here the height is 4. So then what do? I'm supposed to build my polytope p hat, and the way that I do that is by taking my original polytope, which had vertices here, 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 and here. But now I'm going to lift those guys up according to these heights. Okay. So this guy gets lifted to height 1. This guy gets lifted to height 2, so maybe that's over here. This guy gets lifted to height 3. and this guy gets lifted to height 4. Okay? And now we're in one dimension higher. So this is 1, 2, 4. Okay? And so now I get a polytope that has one more dimension. Okay? This is p hat. And now what I'm going to do is I'm going to look at p hat from below. So the way that you do this is that you imagine that you are at a very, very far point down, and you look up. Okay? And if you stand way down and you look up, what are you going to see? Well, you're going to see something that looks like this. You see this point. You see this point. Now, the thing is that you see this point and you don't see this point. Right? And so what you're going to see is that you're going to see this guy. I mean, from down here, this looks flat. It looks like a straight line that's cut right here. And this is what you're going to see, p sub h. Okay? So the original polytope was this one, right, this line segment. And what this process does is that it subdivides it into 2 segments. Okay? So maybe this will be actually a little bit clearer if I do it in one more dimension. Okay? So let's say that we have now a square. And let's say that my heights are given by 7, 5, 3, 10. Okay? So what are we doing here? We're going to build a polytope p hat. And the way we do it is the following. So p lives on the plane, right? So here's the plane. And then maybe here is our polytope p. Okay? But now this thing lives in 3 dimensions. So what I'm going to do is that I'm going to lift according to these heights, right? So then I take this up to height 3. I take this one. Let's see. I try to do this more or less to scale. So this is to height 3. This is to height 5. This is to height 7. And this is to height 10. And so what I get now is a tetrahedron, right? And this tetrahedron looks like this, and now the key point is which way does it face? And you'll see that it does this. Yeah. Because 10 and 7 are way up according with respect to 3 and 5. Okay? So now what are you supposed to do to get pH? What you're supposed to do is look from below. Okay, and so what you see is your polytope P. But now you see a crease in it, you see? And the crease that you see is between the guy of height 5 and the guy of height 7. This is the crease that you see. The crease between 3 and 10 you don't see because that's from the top. Okay? You only look at the stuff from below. And so what you're going to get is the subdivision. Well, I'll draw it like this, and this is the crease that you see. Wait. 3 and 5, I'm sorry. Yeah. 3 and 5 is the crease that you see. And so the subdivision that you get is this one. You get a triangulation of your square. Okay. So this is a nice geometric way of constructing triangulations. These are called the regular triangulations if they happen to be a triangulation, if all the cells are simplices. Or if they're not all simplices, then we have to call it a subdivision. Now, I think with the time that I have left, instead of saying this in equations, you can see I described mathematically all of this stuff. I mean, maybe I'll just tell you that the thing is basically what you do. The way that you make this precise is the following. You start with P, that's precise, right? You start with H, that's precise. And I did define P hat correctly, right? I'm just defining a polytope by telling you where the vertices are. The thing that I'm being very hand-wavy about is this whole business of looking from below. So what does that actually mean? What you're going to do is you're going to look at this polytope P hat, and you're going to look at the facets. And what I claim is that each one of these facets, you can decide whether it's a lower facet or a higher facet, or an upper facet. How do you decide that? Well, for example, what you guys are telling me is that this is a lower facet. Okay. And how do you know that? Because it points down. If you look at the outer normal, the last coordinate is negative. And that's how you decide if a facet points down or points up, is you just look at the last coordinate of the normal and see if it's negative, you call it a lower face. If it's positive, you call it an upper face. Okay. So now you just have to do a little bit of an exercise in cross-hatching, where you take, so my two lower cells in this case are that one and this one. Okay. And the point is that if you now take those lower facets and you project them down, that is going to be your subdivision. Okay. And the projection is well defined. You just forget the last coordinate. Okay. So you look at the lower facets here, and you project them. The projections of the lower facets triangulate P. Okay. So that's a bit of a more precise definition. And if you want to see this written out, then it's in the notes. Okay. That's a regular subdivision. Okay. Now, maybe an example that is even more relevant to us is this example that we had. Maybe I'll do that over here. The example that I did last time of a cone. And this looked like this. Does that look familiar? So this was a semigroup. Those were the generators. They were the points 1, 1, 2, 1, 3, 1, 1, 2, and I guess it was 7, 2. Okay? And Q was the semigroup generated by these guys. Now, remember that I described for you guys the initial complex of this guy. We did this explicitly last time, and we said that the initial complex of I sub L looked like this. When I chose the weights to be 1, 10, 100, 1,000, 10,000. So this is what we did last time. Last time last time we did this for this very concrete ideal and this very concrete weight vector. And the way we did it was just to go through the whole computation, right? We started with Q, I sub L, and W. We computed explicitly the initial ideal. We took the radical. We computed the simplicial complex. But what I want to show you is that there is a very geometric way of seeing this in terms of regular subdivisions. Okay? So one way of getting the same answer is the following. You're going to consider this cone, and you're going to give your generators heights. And the heights are going to be given by these numbers. Okay? So I want you to imagine that I take this cone and I put it in one dimension higher using these heights. Okay? So I'm not even going to try to draw this, but the point is that this guy has height 1. Let's say that the third dimension is coming out of the board. Now let's say it's going that way because I want you guys to be standing below, so you can look from below. So the height goes that way. So I give this guy height 1, so he's pretty close to the board. I give this guy height 10, so he's very far. This guy 100 is really far. This guy is really, really far, and this guy is really, 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 really far. Yeah? And now, what do you guys see? What you see is this thing that looks like this. I hope you can. Yeah? You see creases along each. You see a fold here, a fold here, a fold here. You see a fold on each one of those guys. Okay? So the point is that you are going to use W to get a regular subdivision, which I'm going to call C sub W of the cone C. And what I'm claiming is that if you look at it in this example, then what you see is folds along each one of these guys. Okay. What if we do a different example? What if, for example, well, punchline, this picture is this picture. You just connect whatever you see here. Okay. So let me write that out. Theorem for W